This program is a presentation of UCTV for educational and non-commercial use only.
Welcome to this edition of UCSD Guestbook. I'm Richard Somerville, Professor of Meteorology at Scripps Institution of Oceanography here at UCSD. My guest today is Professor F. Sherwood Rowland, who for more than 30 years has been on the faculty of the University of California, Irvine. He's an extremely well-known atmospheric chemist who shared the Nobel Prize for Chemistry in 1995 for his work on substances that might deplete the ozone layer in the stratosphere. Sherry Rowland, welcome.
Pleased to be here, Richard.
How did you first get interested in the chlorofluorocarbons?
The beginning of that interest came in a more or less innocent way, that the compounds were found to be in the atmosphere and in an amount that was more or less the amount that had been manufactured up to that time. And so it seemed like an interesting chemistry exercise to see if we knew enough from the laboratory measurements, if we could predict what would happen to them. And so that was the origin of it.
Now these chemicals, including common ones that the public knows under names like Freon, are entirely man-made, that's right? So we had a complete record of all the sources.
They had a record as well as you could get from industry, which is really a quite good record. The chlorofluorocarbons are the materials that were used at that time, which is the early 70s, primarily in the United States as propellant gases for aerosols, but also in the blowing of the polyurethane foam, where you would see in your seat cushion of an automobile, in the air conditioning of the automobile, in the refrigeration in your home refrigerator, and in the late 70s and on into the 1980s as material for cleaning microelectronics, the things you'd find in your stereo components and so on.
So they were very valuable, useful industrial gases, thought to be entirely benign.
That was the reason. The reason that they were in such wide use was that they were technologically very valuable because they were inert. They are inert. And of course, that's a key also to what happens to them in the atmosphere. But they were originated in the search for refrigerants that would not have the deleterious properties that ammonia and sulfur dioxide, which were the refrigerants of the 1920s, early 1930s, as refrigeration was just being invented. And CFC-12 became the refrigerant of choice all around the world.
What was it that first suggested the connection to ozone?
Nothing. That is, the procedure was, in fact, that I asked for the United States Atomic Energy Commission that had been supporting my research for about 14 years then, if it was all right to use some of this to look into what would happen to the CFCs. It was a one-page description as part of a much larger research proposal. It did not mention ozone because all I was saying was we'd like to figure out what was going to happen to it. And when Mario Molina joined my research group in 1973, I offered him several research problems, and the one that he chose was to look into the chlorofluorocarbons to see what would happen to them. He was not an atmospheric chemist. I was not really an atmospheric chemist. I had been interested in it dating back to my graduate student days at the University of Chicago, where I did my PhD work with Willard Libby, who won the Nobel Prize in 1960 for the invention of the scheme of carbon-14 dating. Mm-hmm. And carbon-14 dating is an atmospheric problem. You produce carbon-14 in the lower stratosphere, the upper troposphere, and it reacts and eventually becomes carbon dioxide. And that gets taken up in photosynthesis, and all the living materials then take in radioactive carbon-14 and can be used in that way to find out how old a particular object is. Well, this, as a chemist, it was interesting to see how chemistry and physics could impact other fields. And so I'd always had that as a background interest, but not really actively involved in it.
Now, Mario Molina, who with yourself and Paul Crutzen shared the Nobel Prize last year, was just a young postdoc at the very beginning of his career. What was it like? How did the collaboration work between the two of you? Who did what, and how did you work together?
It was basically Mario started out looking at all of the possible things which you think might happen in the lower atmosphere. That is, what we call tropospheric sinks, removal processes that go rapidly. I'll give an example. For instance, molecular chlorine is a green gas. The fact that it's green means that it interacts with visible radiation from the sun, and it lasts about an hour in the Earth's atmosphere. Hydrogen chloride, another chlorine compound, is transparent, so it doesn't react with sun, but it does dissolve in rainwater and rains out, and so on. And Mario went through all of these, and basically we didn't think that there would be a sink from among those. And it turned out that everything you looked at was really very slow. And that eventually turned it up to the question of where else, and we always knew that we would have to do the stratospheric calculation if there were nothing before. And so, after having found that there were no tropospheric sinks, then we started in on the stratosphere. And it became clear that their lifetime, the CFC lifetime in the atmosphere, are of the order of a century or so. Mm-hmm. And then, just to be complete, we talked about it, as a matter of fact, saying, well, we probably know more about what's going to happen to CFCs in the atmosphere than anyone else. We could write this up. But we said, well, to be complete, let's find out what's going to happen to the chlorine atoms that are released when the CFCs break up in the stratosphere.
So you already knew that once the CFCs rose out of the lower atmosphere into the stratosphere, that they were subject to being photodissociated, to breaking up by sunlight.
Any molecule that has two atoms in it is going to break up some altitude in the atmosphere. Question is, what altitude? And it turns out that the ozone that's in the stratosphere protects not only us from ultraviolet radiation, but it protects the CFCs against the ultraviolet radiation. And so it isn't until these molecules rise above most of the ozone layer and most of the atmosphere that they get exposed to the very short wavelength, harsh ultraviolet radiation coming from the sun. And then they break apart and you get chlorine atoms.
At that time, had this been measured? Were CFC concentrations in the stratosphere known, or was it?
At the time, there were no measurements of any chlorine compound anywhere in the stratosphere. So it was all based on analogy with other molecules. And of course, one of the questions that's often raised still after 20 years of measurements of CFCs in the stratosphere, they say that they're heavier than air. How can they possibly get up? And as a meteorologist, you know that the mixing processes don't go by molecular weight until you get far above the stratosphere. They go in large masses of air, carrying everything, light molecules and heavy molecules alike.
So at the time that you were doing this work in late 1973, it was entirely theoretical work. You weren't making measurements as you went along.
The only measurements that we made before we published were using student laboratory ultraviolet spectrometer to measure the cross-sections for the chlorofluorocarbons. They had been measured before, but it was clear in the published material two things. One was that there was something wrong with their data because it didn't quite match, and the other was that they stopped right in a critical region. Mm-hmm. And so with the Carry 14, it's a standard undergraduate laboratory apparatus, we measured these and then could plug these into the model that we had and calculate where this would happen.
So in 1974, you two published in Nature the theory that chlorofluorocarbons might lead to ozone destruction. What was the initial reaction of the scientific community and the industry that made them so profitably?
Well, we published in late June, and the initial reaction was absolutely nothing. The material, there was we gave a press conference in Orange County, and it didn't make it to Los Angeles. There was an announcement by Reuters, the British news service, of the paper in Nature, but it didn't give the names of the people that were involved. Said University of California, didn't say Irvine, and so nobody could follow up on it. And it wasn't until several months later when there was a press conference in organized by the American Chemical Society, at which Molina and I were both giving papers. And at that press conference, then it was picked up by by Associated Press, and it ran then, and it hit the front pages and stayed there for some time. And as soon as it really became widely known, then there was quite a resistance generated, especially from the aerosol industry, but also from the manufacturers of the CFCs.
Now, it wasn't until about 10 years later that the ozone hole in Antarctica was discovered by a British party under Joseph Farman.
Yep.
That was a sudden loss of ozone, more sudden than had been contemplated by the original theory, or was it consistent with the original theory?
The original theory didn't say anything about reactions that would occur on surfaces. We didn't know anything about reactions on surfaces. We didn't know, at that time, the community didn't know about the existence of these surfaces in Antarctica, and the reactions which occur on it were also unknown. So that we said only about what would happen by the molecules in the gas phase itself, and subsequent experiments and measurements in the atmosphere have shown that that part of the calculation was correct, but it was incomplete because it didn't include any of this, the very large effect that's now called the Antarctic ozone hole that appears every September and October.
What was your initial reaction when you learned about the ozone hole?
The reaction was wondering who these people are, in the same way that when Molina and I published, the people in atmospheric science, I wonder, who are these guys? And it wasn't until about 2 months after the publication that I ran into Brian Gardner, who was one of Farman's colleagues, and I realized this was a first-rate scientist and you ought to believe what they said. And then another month or so, I saw the data that came from the satellite measurements, which clearly showed that between 79 and 83 there had been a massive change in the ozone over Antarctica. And then there, of course, this created a tremendous flurry of activity, both theoretically and experimentally.
So in a way, we're looking at a typical classical history of science story. We had a theory and then an observational and experimental evidence promoting the theoreticians to go back and look at new theories and then to make new observations. And
there's a certain serendipitous aspect about it too, because the important part was not contemplated in the original description. We just said we'd like to find out what would happen to the CFCs. We didn't say we think it's going to be important environmentally. It was the discovery that the chain reaction occurs in the stratosphere, in which the initial chlorine atom reacts with an ozone molecule, giving chlorine oxide, and the chlorine oxide gets recycled back to chlorine atom and takes out another ozone. And in fact, every chlorine atom takes out about 100,000 molecules of ozone. And it was this change from 1 million tons of CFCs released to the atmosphere every year, which was characteristic of the 1970s and the 1980s. But 1 million tons isn't enough to create a major effect in the atmosphere until you multiply it by a chain length of 100,000. And when you do that, then you're putting it on a global scale that's competitive with the natural processes. And it's when we realized that it said, changed what had been an interesting scientific exercise into a major environmental problem.
And if we jump ahead now, the theory and the discovery of the ozone hole and all the additional work that's gone on have led to an international agreement, a series of agreements to phase out chlorofluorocarbons and related chemicals. From your viewpoint, how successful have those international agreements been?
Well, the international agreement itself is called the Montreal Protocol because that's where the meeting was held, at which they announced in 1987 that they were calling for a 50% reduction in the amount of chlorofluorocarbons manufactured and released to the atmosphere every year. They modified this again in 1990 to say 100% by the end of this century, by the year 2000. And then they modified it in Copenhagen in 1992 to say 100% reduction by January of 1996. That is 8 months ago. And the measurements in the atmosphere itself have shown that the Montreal Protocol is working extremely well. the amount of chlorine that will eventually go up into the stratosphere has already reached a maximum in the lower atmosphere. And that's because of the search for substitutes, and when they find a substitute, then the compound that was being used goes out very quickly.
And how optimistic are you about the long-term health of the ozone layer? What time scale can we look at for recovery of the natural concentrations?
The time scale is dictated by the lifetime of the chlorofluorocarbons, and the longer-lived one, CFC-12, this is the refrigerant in your home refrigerator and your automobile air conditioner, has a lifetime measured now in the atmosphere of about 100 years. So we're talking about important amounts of CFC-12 being in the atmosphere all through the 21st century, all through the 22nd century. The ozone hole itself probably should be mended by sometime late in the 21st century. I don't know, 2060, 2075, something like that, because these are very long-lived molecules.
All right. And is there a sign yet of an illegal manufacturing industry of black market chlorofluorocarbons? Are you concerned about that?
There is a black market. It's probably not illegal manufacturing. It's probably, there was a provision, well, it may be illegal because some of it is supposedly coming from Russia, and Russia was under the original terms to have stopped in January 1st of '96. The third world countries are allowed 10 years to phase out their use of it. And so there may be some coming in from third world countries where it's intended for their own use or not to be sent into this country. I don't think that it is a major problem in the long run. It's certainly there are reports of its black market at the present time, but the chief place that the black market is going is into automobile air conditioners. And the automobile air conditioners since 1993 in the United States use a different compound and are built around that other compound. So it's only the older cars that want fluorocarbon 12, and every year those cars get older and go off the road. So that this is a black market that has a sunset clause in it, that it's going, no matter what people want to do, they're not going to want to get fluorocarbon 12 and put it into a car manufactured after 1993. So within a decade or so, almost all of that demand will have faded away. Incidentally, there are also substitutes that work quite well that are available on the market at the present time. So at some point, the substitutes will probably cut into that black market too.
Now, the original chlorofluorocarbons, when they were first invented in the late 20s or early 30s, were thought to be entirely benign, to have no harmful effects. They were a miracle chemical, as you've said. They made refrigeration safe, and they found many uses. How confident can we be that the substitutes that are now being put in car air conditioners, for example, are safe and don't have unanticipated consequences?
One is always hesitant to say that nothing possible can happen with it. I think these compounds have been more thoroughly investigated than any other compounds that have ever been put into use in society. The companies financed studies done by quite a number of academic and governmental institutions looking to see what the problems might be, and there were no showstoppers among these problems. Some of them do contain chlorine. They contain chlorine in small amounts, so that it may be 3% as much problem as one of the CFCs. But even these are scheduled for a phase out early in the 21st century. And so there will be other substitutes coming in for them. So I think that this is probably a closed book as far as the environmental problems. Some of the proposed compounds were found out to have toxic effects, and so they were discontinued. But the ones that survived, that both the atmospheric chemists and the toxicologists tests, are the ones that are in use now.
I can't help asking you about the Nobel Prize, which you received in fall of 1995 together with Mario Molina and Paul Crutzen. It has such mythic stature in the world at large, and certainly among scientists. How did you react to the news, and what
I would
difference has it
suspect
made?
I suspect that almost everybody reacts favorably to the telephone call from Stockholm. I mean, so it was, clearly it was a very enjoyable aspect. Actually, going the week in Stockholm is a very remarkable event and extremely enjoyable just as a social occasion. In this particular case, because Paul Crutzen is an old friend, and of course Mario is a friend, and each of us took along other people that had worked on the problem, and there's some people in Sweden. So we had the ceremony itself is on December 10th, but on the evening of December 8th, all of us got together at the home of one of the Swedish atmospheric scientists, and that was really a very, very pleasant party. One of the people who came along with me was Ralph Cicerone, who's now the Dean of Physical Sciences at Irvine, and who, with his colleague Rich Stolarski, had found out this chlorine chain reaction back in 1973. But Molina and I discovered it ourselves, but we found out we're not the first to discover it, but we plugged it into the chlorofluorocarbon problem.
Let's talk a little bit about the future now. Tell me where you're putting your efforts now in research, and what are your concerns about environmental problems of the future?
Our effort is being put into more into tropospheric chemistry, that is in several ways. We have been collecting air samples in the middle of cities. In Mexico City, for instance, we found that there's substantial amount of hydrocarbon concentration there coming from the liquefied petroleum gas, or LPG, that they use for heating and cooking. That's also true in Santiago, Chile, where we've been doing experiments. We've been flying on the NASA DC-8, collecting air samples in various places around the world. We were in South Africa and Brazil in 1992 looking at the biomass burning, that is when they're burning off their agricultural or forests, and flying through the plumes from that. So that's been that's an area where we're doing more in terms of science right now. If you ask about environmental problems, I'm certainly concerned about greenhouse gases. And of course, at UCSD, you're coming to the home investigation here with Dave Keeling's measurements since 1958 on carbon dioxide, and the measurements on N2O that were started by Harmon Craig and then by Ray Weiss going back even to 1964. So there's been a long history here at UCSD of measuring the greenhouse gases, particularly the gases that like CO2 and N2O that are increasing in concentration. And ultimately, the growth of population around the world carries a lot of environmental potential consequences, because all of these people want to have a better standard of living, and all through the 20th century, the way you got a better standard of living has been to use a lot of energy, and energy has waste products, of which carbon dioxide is certainly one of them, and even alternative energies like nuclear also have waste products that people are concerned about. So how we solve the problems of the 21st century in the face of population growth will be, there's plenty for all of us to do.
I certainly agree with you. In an area like this, where science bumps up against public policy and everyday concerns of people, are you worried about the problem of scientists becoming involved in the political sphere, as you had to do in the chlorofluorocarbon case, and about the general issue of science literacy among the general public and an awareness of how science impacts our lives?
It's a tricky situation that in a democracy you think that things would be decided by everybody, but you wish that they knew more if they're going to make decisions about something which has a high technological content. And so it's a tricky problem as to how much time you spend in the laboratory and how much time you spend talking to someone else about it. Certainly there were a couple of periods of time when we were spending a lot of time talking to Senate and House committees, to state legislatures, to television, radio, magazine, so on. I think it was absolutely necessary to explain why it was. It was very easy to think, what do you mean my aerosol deodorant can have a global effect? How does it ever even get out of the bathroom is the kind of thing that one would hear. And you just have to explain that there are scientific facts that get involved in this.
Now, in the case of chlorofluorocarbons, there was a smoking gun in the form of the ozone hole. There was a technological fix in the form of benign substitutes. There was an international willingness to outlaw the offending chemicals. And in a sense, it's been a great success story, a kind of paradigm. Do you foresee something like that happening in the case of the greenhouse effect? It's a much more difficult problem.
It's and it's not necessarily encouraging. I think on the international basis, on the CFCs, the first push to control in the mid-1970s took care of the aerosol sprays, but only in the United States, Canada, Norway, and Sweden. And then, but aerosol propellants, CFCs, were used from then on. It wasn't until you found a major unexpected problem, the Antarctic ozone hole, that the agreement consolidated for all CFC uses and for all countries. I hope it doesn't take some similar discovery of a totally unexpected effect in the greenhouse case to get similar kind of cooperation. But I don't think the precedent is necessarily very cause for optimism. It didn't happen until the Antarctic ozone hole appeared.
What's your advice to governments and policymakers today when it comes to the greenhouse effect? Is it too early to think of reducing emissions of chemicals that contribute to it? Do you favor things like a carbon tax or fuel switching? Or?
I certainly favor a carbon tax, and the governments committed themselves in 1992 in Rio de Janeiro to such controls. It is unfortunately true that anybody who runs for election and favoring a carbon tax will need to find something other than politics as their new profession, because they're not going to be reelected. And I don't know what the solution to that is, except, as you know, we pay far less for our gasoline than anyone in Western Europe or anywhere else except places like Venezuela that are sitting on the gas by itself. It's a matter that we have to somehow get enough education around that we start doing those things which are going to be good for the 21st century, not just for 1996.
The Nobel Prize certainly gives you a bully pulpit for putting forth those views, and I hope that you find listeners for them. Do you find the general public in a way receptive to these kinds of concerns to a degree that politicians are not?
I think the general public is mixed, probably in the same way that the politicians are. I certainly found in talking about chlorofluorocarbons that there were quite a number of senators, particularly from both parties, that were very interested. As a Californian, I could express the regret that none of these senators happened to be from California over the 20-year period that this was under discussion. There were people like Senator Chafee, who's from Rhode Island, a Republican, and Vice President Gore, when he was a senator, were very much interested in these problems. And at the same time, there are people on the other side.
I think we can all agree, at least, that the success of the ban on ozone-depleting chemicals gives us hope for the ability of the world to work together on these problems.
It gives an example. Let's hope that in 10 years from now, it won't be the only example.
Thanks very much. I'd like to thank you, Sherry Rowland, Professor Sherwood Rowland from the University of California, Irvine, who's been our guest today on this edition of UCSD Guestbook. Thank you all.